guys, nice to see you. So last time we considered lenses, in particular what lens represents by itself. It's a combination of two interfaces between, let's say, glass, if we consider material of the lens, with external environment. So usually that is air. So we have transition usually of rays from air, where the object is located. Then it goes through first interface, we have some reflection and refraction. That's the interface. Then it goes inside the medium of the lens, the glass. It goes through the the glass. Then it hits another interface. Now it's glass and air. And then we form the image. So we consider separately two interfaces. The image which is formed by the first interface was considered as an imaginary object for the second interface, and then already second interface with this imaginary object was used to create the image of the whole lens. Also, we took into account the fact that the lens was narrow, and that means that the distance between two interfaces which are taken into account in the lens is much smaller than the distance between the lens and object, and also between the lens and image of this object. So based on this consideration, we derive equation which gives us the quantification of the image formation by a thin lens, which takes into account refractive indexes of the external medium and internal medium of the glass. So we consider that external medium is air, so we deal with unity for refractive index, and refractive index of the material of the lens was given as n. Also, we deal with the curvatures of these two interfaces, defined by radius 1 and radius 2. And we introduced also the concept of the focal distance for a lens when rays hit the lens being parallel to the principal optical axis. Then all of them converge in one point. This point is located at focal distance. It's called focus of the lens, and this distance is given by relationship where refractive index and curvatures of the first and second interfaces. So that is so-called lens maker's equation. Why? Because focal distance is a unique parameter of a given lens, and from the right side we have refractive index of glass and radius of the curvature. So all of these parameters are constant. They are not changing over time, and that's parameters. These are the parameters which we need to know when we design specific lens for our need. So with that, we finish our discussion of the ray optics, and our next topic is interference, and that is a phenomenon which highlights the wave nature of light. As we know, light is actually can be represented in some circumstances as an electromagnetic wave, and interference is one of the unique phenomena which clearly highlights this wave nature. So, what do we need to observe interference? Because if we call interference as superposition of two electromagnetic waves, so that is what's happening actually now with multiple light sources in this room. So we have a lot of electromagnetic waves, they superimpose, so they interact with each other. However, we do not see such periodic patterns of bright and dark fringes. So any ideas what is the reason for that?
Light should be coherent.
Coherent. And coherent means, can you give the definition what it is?
One phase is similar wavelength.
So wavelengths should be first, because that is monochromatic light. As you see here, we don't have like white light, so it's red. So it's monochromatic. There's one wavelength. It should not necessarily be only red. It can be any other visible color, because we are talking about visible spectral range. Another parameter which is important here is phase shift. So you mentioned the phase is the same phase, but in order to see so-called constructive, where light is enhanced, and destructive interference for dark ranges, we need to have different phase difference. And the thing is that for light sources, so it should be constant. Is the phase difference, whatever it is, it should not change over time. And that's why, in order to realize such conditions, well, we can use some advanced lasers. Maybe later this week I will bring you some like different wavelengths lasers, and we'll show something. But we also, like, these experiments were carried out at that time when there were no lasers invented. So how you create two coherent waves, like light sources. So we can deal with some monochromatic light wave, which travels through this opaque screen with two slits. So how we create monochromatic light? Any suggestions? Because let's say light bulbs or solar light, this is not monochromatic light. It's a mixture of different wavelengths.
We need to make it so that the other wavelengths will reflect.
Mm-hmm. So how technically you would do it? So either using some prism when we have refraction, and then this kind of dispersion of white light, because how it works, different the same material possesses different refractive index for different wavelengths. That's why in a prism different wavelengths will deflect at different angle, like refract at different angle, and then you will split the spectrum into different monochromatic wavelengths. And if you place some single slit in front of this spectrum where you want, so it's either red or blue or green light, you can cut like everything else and let this narrow part of the spectrum go through the narrow slit. And then this will be our monochromatic light. So that's how we deal with it. So you can also use some diffraction gratings, but we will talk about them later. I mean, to split white light into its spectrum. Then this light hits two slits which are placed close to each other. The width of these slits should be small, so we start to see some diffraction effect when, like, which causes the spreading of light in kind of shady areas defined by geometric optics, because according to geometric optics, light should just travel straight through these slits. However, because of diffraction, it starts to travel at different angles and goes beyond the shady areas defined by geometric optics. So why? Because in general, we could represent these two slits as two-point light sources, which emit electromagnetic waves of given wavelengths. Wavelengths doesn't change, but in this case, since they are point sources, they travel in all directions in this area. So now what happens? We have actually a coherent combination of two light sources. Because this is monochromatic light, the wavelengths of light emitted by these two point light sources will be the same, and the phase between, like phase difference between them, will be also constant, because this is the front of the monochromatic wave which hits this screen and these two slits. Front, what is the definition of wavefront? It's a geometric composition of points with the same phase. So means every time these two slits will interact with the front of monochromatic electromagnetic wave, and as a result, the phase shift between point light sources S1, S2 located at S1 and S2 will be the same. So it will not change over time. So these are the conditions when interference can be observed. So now, if we consider maybe go to another slide. As you saw from previous slide, we have these conditions of constructive and destructive interference. Constructive when waves are approaching some point on the screen in the same phase. In that case, they enhance each other, and the amplitude of electric field, for instance, of the electromagnetic waves, and thus the intensity, because we know that intensity is proportional to square of electric field, will increase because they approach this point in the same phase, they overlap one over another, and as a result we get twice larger amplitude of electric field of these electromagnetic waves. Why it happens? Because now the distance which electromagnetic waves are traveling from both slits to a given point on the screen will be the same. So these two waves are in phase, they have the same phase, they travel the same distances to point O, and that's why in this point O location on the screen they also remain in the same phase. If they're in the same phase, they enhance each other and create so-called zero order interference maximum. So this will be the bright fringe at the center. Yes?
So, like the zero order maximum, does it have a bigger intensity than the second one, than the next bright function, the first one?
Well, yes, but for intensity distribution between orders of interference, we will talk a bit later. Also, we will involve distribution for light intensities for diffraction. So we will discuss it a little bit later. But now we just define the conditions for maximum, constructive, and destructive interference. So now let us consider some point P on the screen, and in this case, you see there is some difference in distance this waves should travel. And difference in distance means that the phase difference between these two waves in given point P may be already different from the phase difference between these waves at slits S1 and S2. So depending on the difference in traveling, means on the position of this point P, it can be moved along the screen. We may have several conditions. So first condition, when the difference in the path which these waves are traveling will be equal to integer number of wavelengths. So if there is some difference in traveling distance, if we can divide this difference in integer number of wavelengths, then the wavelengths, the waves will approach this point P in the same phase also, because we know that wave is actually a periodic process. If it happens that the difference in traveling is one wavelength, then it comes back to the same original position. So there is no difference of phase shift between points S1 and S2, and actually point P for both waves. What it means, we also get constructive interference, and that will correspond to bright fringe on the screen. So we have this bright fringe on this position. However, since we can move, like pick up any point on the screen at a different angle position or linear position, how you prefer to define, it is possible to find such position of point in the screen when the difference in distances which these wavelengths are traveling will be equal to odd number of half wavelengths. In that case, we will have a situation when waves will approach given point in opposite phases. Since they have the same magnitude, the same amplitude, because the slits have the same width, they approach this point in different, like not in different, but in opposite phases, specifically important. And in that case, they will just cancel each other. So electric field vectors will be of equal magnitude, but in opposite directions. So they cancel each other, and as a result, we get dark fringe. There is no visible light in this area. So if we consider not as a point but as a plane, then we will end up with dark and bright fringes, which were shown on the previous slide. So let us go to another slide, and we'll come a bit more specific here before we add some equations. So this is the same model. We have monochromatic light, the screen with two slits, some point P at the screen. So we can define this position of point P, as I mentioned already, with angle theta. So it's like angular position of point P with respect to the horizontal line which goes through the center between two slits, or with linear coordinate y. So there are two options to define position on the screen, either angular or linear. So from this yellow triangular, we see that the difference in distance which rays R R2 is traveling with respect to ray R1 is defined by this delta, and this delta will be distance between two slits. Let's consider that will be some d times sinus angle theta. So this is the difference in distance these two rays are traveling. So we will deal with this parameter, and from this figure, it's clearly seen how we can quantify it. So if we look at this figure next to it, we see that the difference in the distance ray R2 and ray R1 travel is d times sinus theta. So when we know already all this information, let us go to our whiteboard and get some equations.
So the
Mhm.
black fringe is from the face, and the dark is from the opposite faces. But what if the outer face is not by like 50, but like 5/4?
So in that case, that's one question which we are going to discuss right after introducing the main equations. That so far we consider only bright and dark. However, that's not the case. We don't have just bright and dark. Within bright, we have some intensity distribution, and within dark, we also have some intensity distribution. So what now we will give these conditions, like write equations for conditions which we describe with this in phase and out of phase. And those are the coordinates, angle or linear coordinates, specifically for the center, for the brightest part of the bright fringe and the darkest part of the dark fringe. But there will be some light intensity distribution. We will talk about this. So we will quantify it. So, as we already discussed, the condition for a bright fringe, to be more specific, for the center of the bright fringe, can write d times sinus theta bright equals to m times lambda, where m is equal to 0, plus minus 1, plus minus 2, and so on. So how would we define the condition for the dark fringes? D times sinus theta dark. We mentioned that it should be like odd number of half of wavelengths. So that will be m plus 1/2 times lambda. And that will be m equal to 0, plus minus 1, plus minus 2, and so on. So these are the conditions for constructive and destructive interference when exactly we have this in phase and out of phase cases. So if we come back to this slide, so here we would like to also describe it not only in angular position, but also in linear. So for that purpose, we need to consider this distance between the slits and the screen. So there's some capital L. And once we consider it, we can write this angle theta, which we defined in our previous equations for constructive and destructive. It can be also described as ratio between y coordinate, this distance from 0, and distance between the slits and the screen. So let us come back to whiteboard. So we can write tangent theta is equal to y over L. And taking this into account, we write that y bright, linear position of bright fringes, will be given as L times tangent theta bright, and y dark, L times tangent theta dark. So if we assume that this angle theta is small, then we can write that tangent theta is approximately equal to sinus theta. And in this case, we can replace this tangent theta with sinus theta, so we can write that y bright, linear position of bright fringes, will be given by capital L times sinus theta bright, and that will be L times m lambda divided by t. So for this sinus theta bright, we get expression from here. So it will be m lambda divided by d. And y dark, position of the center of the dark fringe, will be given as L times sinus theta dark, and that is equal to L times m plus 1/2 lambda divided by d. So these are the relationship which provide us information with the position of the central part of the dark and bright fringes, destructive and constructive interference conditions on the screen in both cases, either angular via angle theta or linear via y. So obviously, if you don't know distance to the screen, you cannot operate with linear, but you still can define these conditions with angular position.
The L is
Capital L is the distance between the slits and the screen where you actually observe this interference picture. So now we coming to this question that actually it's not only dark and bright, but there is some light enhancing distribution. So in order to answer this question, let us consider two electromagnetic waves, in particular their electric field time dependence. So it will be wave 1, E1 is equal to E naught times sinus omega t, and E2 will be equal to E naught times sinus omega t plus phi, which is some phase shift between them. So now, and this phase shift phi can be arbitrary. It shouldn't be either 0 or pi. So it should be it can be any phase shift. So now we know that the delta, the difference in passes which waves are traveling, is given as R2 minus R1, and that is d times sinus theta. So if delta is equal to lambda, then what will be the phase shift? Phi. So if delta is equal to 0, phase shift is 0, because there is no phase shift. If delta is equal to lambda, phase shift is 2 pi, because it's like complete cycle. So it's 2 pi radian. So taking this into account, we can write in general that the ratio delta over lambda, so it's dimensional ratio because both are distance, that is equal to phase shift phi, some arbitrary phase shift phi, divided by 2 pi. And from here, we can write that phi, phase shift arbitrary value will be equal to 2 pi over lambda times delta. So it will be defined by the distance between these position vectors r1, r2 from slits towards the point where we observe the interference, the superposition of these two waves, and this difference will define phase shift with this relationship. So you see that here we have lambda in the denominator. So if we consider just monochromatic light, then this is constant parameter. However, if we change the wavelength, so let's say we move this prism and through original slit we let not red but green light through, then for the same difference in distance which two rays should travel, we will get different phase shift. So that means if we keep everything the same, we just change the wavelength, the interference pattern obviously will change because the conditions for angular position for destructive and constructive interference will change. And this delta, as we know, we can express as 2 pi over lambda times sinus theta. So now we want to have a superposition of two waves. So we consider some resultant electric field E in point P, for instance. That will be E1 plus E2. And that is E naught times sinus omega t plus sinus omega t plus phi, and close the parentheses. So now this is the expression for the resultant electric field because of superposition of two coherent wavelengths with different phase shifts, with some phase shift phi. We can proceed further, taking into account some trigonometric identity. So in general, we can write that sinus A plus sinus B will be equal to 2 sinus A plus B divided by 2 times cosinus A minus B divided by 2. So that is general form, and here we will consider that A is equal to omega t plus phi, and B will be equal to omega t. So when we do these substitutions, we can actually get the distribution of electric field in this point, of the superposition at a given point of two waves as 2 E naught times cosinus phi over 2 times sinus omega t plus phi. So this is the distribution of electric field as a function of time and phase shift. And here we have the amplitude. So there is this parameter is time independent. So that is actually our amplitude so of the electric field, and this is 2 times E naught cosine phi over 2. So the maximum amplitude will be defined when phi is equal to 0. So cosine 0 is unity, and if we consider just this part, amplitude will be 2 E naught. So that's what we discussed when we have this specific case when the uh, two waves are in phase, there's zero phase shift, their electric fields will enhance each other and we will have twice larger. But that is specifically true for the central, the brightest part of the uh, bright fringe. If we get condition for cosine 0, then obviously, so when they are in the opposite phases, then obviously the amplitude will be 0. So nothing here already doesn't make any difference because amplitude is 0. So that is the darkest part of the dark fringe as the interference pattern. But obviously, this is not just in phase or out of phase. It can be any arbitrary number. That's why we have this distribution, and we don't have much time left, so we will start next time from this equation. We will go further. We'll make a transition from electric field to light intensity because that's what our eyes and other measuring equipment or devices are dealing with. We are always dealing with some integrated average light in, amount of energy transferred per unit time per unit area. So we deal with intensity, and that's why we need to go from electric field. We know that intensity is proportional to electric field in second power, and then once we already have intensity, we can integrate it over the period in order to get some average intensity. And eventually we will get the relationship between intensity and angular or linear position along the screen where we observe interference. So that's our plan for next time. Today we introduced the concept of interference, which reveals the wave nature of light and define conditions quantitatively, which will satisfy constructive or destructive interference, and that corresponds to bright or dark fringes on the screen of this interference pattern. Our goal for the next discussion to finish with this distribution of light intensity all over the interference pattern. To be more specific, that we will be able to tell how light intensity changes within the bright and dark fringes of the interference pattern. Okay, thank you very much for attention. See you next time.